Okay, I'm going to start the advanced HIP. Is everybody feeling a little more comfortable with OpenMP and see how you can find out what the compiler is doing? I think that's crucial to actually writing a real application with OpenMP. So at break, I wanted to see if I could get everybody to go out front and we could get a picture front of the sign for the building, so that we can show that Japan is actively doing some GPU programming. I'd appreciate it. I got a picture yesterday, but people are too spread out. It didn't look quite as impressive. Okay, so we're going to dive even deeper with the HIP programming. You have more control with HIP. Yes, if the compiler could give advice which pragmas to insert. This is an area where actually an AI programming assistant may be helpful. Also, I go into more detail on OpenMP on the CPU in my book, and I see people using way too many pragmas for shared and private that are really not necessary, and they end up with like 10 lines of pragmas or clauses about all the variables in their loop. And one of the rules of thumb is if it's on the right side of the loop, you don't care if it's private or shared. Only worry about things that are on the left side. So it doesn't matter if they're private or shared if they're on the right. But yeah, there's it would be helpful if you got a little bit more guidance, or if the compiler was smarter on how to handle things and gave you warnings. One of the things I would really like to see, either from the compiler or the standard, is what do I do if it's wrong? Am I required to spit out a warning? The standard doesn't say that. And it would be helpful that it warn you or give you an error rather than just try to run with it. I think that's one of the big limitations on our when you're trying to program with these languages, the pragma-based languages. Okay, so we're going to look at basically the performance limiters for a kernel. This applies for OpenMP as well. It's just that you can't see it as easily in OpenMP. So, you know, basically on GPUs, they're high throughput devices. They are designed to run thousands of simultaneous work groups, each with 64 threads. So you have to have a lot of work to keep a GPU busy. We really want all these compute units with work to do. One of the reasons is when on a GPU, if one of these work groups, it's a stall operation, for example, a memory load, it's going to swap to another piece of work to be done. GPU can do a swap between those items at zero cost. So there's no cost to switch like on the CPU. And so we want a lot of extra work on the GPU so that it has something to switch to. That's what's often called occupancy. It's been over discussed in optimization for GPUs, and it's simply having enough work so that you can switch to it when you hit a stall. So we have several different performance limiters. We have memory bound and compute bound. It is very hard to get to the compute bound limit. The balance on these GPUs and even on the CPUs is approaching 100 flops per per double loaded. It's hard to find a kernel that actually does that much work. A matrix multiply is around 62 flops per double loaded. And it's heavily optimized to get to that point. So it's very difficult to get compute bound, and that's why we say flops are free. Most of us numerical people think flops are the work. They're free. It's the memory movement that is your limiter in almost all cases. Now, where is your memory? What am I talking about memory movement? We're saying bandwidth, but it's also network. It's also disk, which are even slower. So that's going to be your biggest bottleneck on your system, is memory movement. You need to line up your data so that the processor can operate it as quickly as possible. If you're jumping around in memory, you're latency bound. And there are some applications that are latency bound, and some of them are poorly written, and some don't have a choice. You don't want to be in latency bound if you can rewrite your application so that the data is streaming into the processor. Okay. Now I like to talk about this concept of data-oriented programming. So there's a lot of discussion of object-oriented programming. Object-oriented programming is writing a program quickly. In HPC, we want to write a program that operates quickly. We don't care if it takes more time to write the program. That's different than 90% of the programmers out there. They just, can I deliver it by Friday for my customer? And you can see it in browsers now. They haven't increased in performance for 20 years, even though our computers have gotten more powerful. And they keep using up more memory, right? And it's because current hardware allows you to be a sloppy programmer, except within HPC, where we have to pay attention to that. So let's look at these performance limiters and see how to judge where we are for our application. And a key metric is arithmetic intensity, which is the number of arithmetic operations per byte loaded. Okay, so this is what we call feed and speed. So can I get the data there to operate on? Keep those compute units busy. So that brings us to a roofline. And this was really a big breakthrough when they came up with this visual view of the performance of your application. The roofline is a horizontal line for compute bound and a sloping line for memory bound. And I can remember when the US government, the Office of Management and Budget, would come to Los Alamos and they would look at our use of the computers and they'd say, well, you're way down here at 1% of compute performance on the system. And then it kept dropping. And they say, well, why do you need a new computer? You're not using it. The problem was we're memory bound. So this made it much easier to explain to them we were actually getting good performance for our application. So this is really important to get that visual view, especially for those who are not as familiar with the hardware. And so most of our applications are in this memory bound region, but we can sort of be moving over a little bit into the compute bound and need to worry about compute bound as well. Want to be close to these roof lines, that tells you you're getting good performance. But I'll note, this is log scale. If I were at this point here, that's still a long ways from that roof. And then it's a question just how valuable it is to get a little bit faster. And I've had codes where we had to hit a performance number for for an acceptance test. Well, it may be worth weeks of work to get a little bit bigger boost. But if I were to run that code, I don't care. I've done enough optimization. So it's dependent on your use and what your goals are. Okay. So you'll see this chart, and we can generate that chart with our profiling tools. But you can also take that estimate like we did for the alignment, say, where are we here? And just plot the point. You don't need to have any fancy tool to do that. Okay, so let's look at memory bandwidth bound. Reducing data movement is just extremely important for GPU performance and CPU performance. So you want to move that data. You want to load a cache line, use all the values in that cache line. Load a page, use all the values in that page. That's easier said than done. We want to reuse data, so we talk about spatial locality and temporal locality. So can we use it in the next loop? Can we use data that's close to us? If we can stage data in registers or our shared memory, or what we call our programmable scratch, programmable cache, that gets almost as good a performance as the registers. And if you can do lower data precision, that can be a big boost in the performance here as well. So coalesced loads and stores, I'm going to do a deep dive on that concept here at the end. L1 cache line size is 64 bytes, 128 in the MI300 series. You need to watch out for strided accesses. Well, we do multi-dimensional. You're going to have strided accesses, right? Show you how to avoid those. Okay, very important, because otherwise when we're doing Y and Z dimensions, we're going to get hit with really poor performance. We can use vector data types. So a lot of people talk about vectorization speeding up the code. But it's not the vectorization that makes things faster in computing multiple things at a time. It's actually the wider memory loads that helps a lot, because it affects the bandwidth. And that's usually our limit, not the compute. So we talked a little bit about aligned memory accesses. We can also use this fancy streaming store or non-temporal loads to store out faster. The compiler will often do that for you. I wouldn't mess with that too much in general. It's a little tricky to use, and if you write out to main memory, you may find the next loop needs it, and you're just going to slow the next loop down. So let's look at what this output is from a utility called Godbolt down here. You can put your code in there, and it will show you the assembler that is generated by your code. Okay, you can look at this and start looking for key things that help you understand what's happening. So here we see a D word, so wider load and store. That's telling us the compiler's generating those wider loads and stores. And that's what we really want, because we don't want to do a lot of messy stuff over in our code to force that. We really like the compiler to figure that out and do it for us. Now, what would affect that? What would help generate those wider loads? Well, things like adding the restrict keyword tells the compiler it can optimize some of this stuff. Now let's look at compute bound. So even though we're usually memory bound bandwidth limited, there's some key things you may want to watch for in your computation. You can pre-compute data and then do a lookup table. But often on the GPU, the math is so fast, if I can recompute it in the kernel, I may want to do that because the flops are free and I want to load less data. Watch for things like, here is taking the A variable and raising it to the power 3. Even on the CPU, this is doing it as in software as a floating point operation. So 3.0 is floating value. And so even on the CPU in C, this is very slow. And so expanding that out, I often use a pragma, a pound define to do that. So it reads well. I can still call it power, but maybe some additional letter or make it capital and have it expand out to this form here. And that'll make a huge difference. And it makes a huge difference on the GPU as well, and it reduces vector registers. The other, I've gotten speed up where we were doing quad roots of variables in radiation. That's fairly common. And by doing 2 square roots, I sped up the code by 50% just from that one change. Because the compiler's not going to optimize that. It doesn't realize that we're physicists and we do these stupid things all the time. So it may optimize a square root, but not quad root. Little things like that can make a big difference. You can also do packed floating point 32 operations in one instruction. There's some tricks to do that as well. So staging data is really important, putting it in the right order so the data's in cache. That can make a huge difference. And then here's our matrix cores and how to use those. And there's a whole blog on that and some tools to help you use that if you want to try to put that in your code. But that's for small matrix calculations. And it does double, single, and lower precision. We also want to watch out, and I see this a lot in code, especially among physicists who may not understand what the compiler's doing. So in this case, we see a lot more output than we're expecting. What's going on here? Does anybody see the problem? The answer's on the right, so it's not that hard. And I see this all the time. So we've got 0.3. This is C code. So that 0.3 is going to force all the other variables on that line to promote double precision. C, we promote double precision for mixed operations. So because that is a double precision variable, all the rest get promoted. Just simply by adding F on the end of that variable, you eliminate, look how many instructions you eliminate. Okay, so being careful about that is really important. Fortran, well, on the CPU, because we're not going to have it in kernel code, but on the CPU, Fortran will demote to single precision if you have mixed types. So again, you want to be very careful about that in Fortran as well. Okay, so that'll reduce ops. Well, we got ops for free, so that may not make a dramatic difference, but it's still good programming practice. And if we were compute bound, that could make a difference. Latency bound, we need a lot of parallelism. So if you're missing on cache, how are you going to hide that on the GPU? I'm going to have work to switch to, right? The more misses on cache, the more extra work I need. Okay, so I need to have more parallelism to fully utilize the GPU while I'm waiting for that memory to load. That'll make some difference, but it's not going to completely compensate for just not loading the data in a preferred pattern. Using synchronization barriers can help. Thread divergence is a big problem on GPUs, and people hear this and say, oh, I can't use any if statements. If they're short blocks, it's not a problem. Where we get into real trouble is like if we're doing a particle code and one particle out of your 64 threads is going through 1,000 more operations than the rest of it. That just kills you. Okay, so short divergence is okay. Large divergence is not. And then we have to really watch out for the register spilling. So the GPU has just a huge amount of resources. And I really think the name of a GPU is wrong. You should view a GPU as a parallel processor. GPU is just the first application it was used for. Okay. I don't even like GPU because it really is a coprocessor for parallel operations. You want to use it whenever you've got a lot of parallel work to do. So we have to have a lot of work, and if we stall the wavefront, which is typical when you're waiting for data to load and waiting at a synchronization barrier. And this is the key why GPUs are so much faster than the CPU. Memory difference isn't all that large. It's a 2 to 4 HBM memory is a little bit higher. But the key is that if I hit a stall, I can hide it. I can hide that memory load. Okay. If I have enough work. If I don't have enough work, it doesn't help. So if I got one work item to do, the GPU isn't going to help me. It's going to hit that stall. It doesn't have anything to switch to. On the MI300A, that may be a good time to do that on the CPU, that one operation. When I got 1,000 things to do, I'll do that on the GPU. So occupancy, there were lots of blogs and optimization guides about occupancy on the NVIDIA GPUs. It's a nice concept, but it's oversold. There's a lot of other things that are important. And here we just want to have a lot of work to put onto those compute units. And we got 100, this is I think an MI210, we got 104 compute units. Okay, so I gotta have 104 separate work groups to launch, but then I got 4 SIMD units on every compute unit. So that's 400. And then I get 64 threads on each one. So you start multiplying that out, and this is showing 32 wavefronts on each CU. We're in the thousands of work that we need to have for those GPUs. The GPUs are so fast, it's hard to keep them busy. It's really, really hard. I thought when I first was doing GPU programming on my laptop, I thought it would time out and the display would freeze up. You can't get enough work on the GPU to cause that to happen. It's just, they are so fast. So our goal is to get as much work as we can on it. So your goal as an application developer is to expose the parallelism, get as much work as possible. And you will find that if you're doing small problems, the CPU is still going to be faster until you reach a certain size that the GPU starts, the crossover point where the GPU starts becoming much, much faster. So here's an occupancy example. If I've just got this much work units that I'm launching, one work group with 64 work items, I've only got one SIMD unit on that compute unit working. If I do one work group with 256 work items, well, I can do four waves then. So I've got a little bit more occupancy. And if I have larger work groups with a lot of work. Now I can fill up the GPU. And that's what we're really talking about with occupancy. But there's other things that are important. This is a very simplified diagram of a compute unit. We have this local data store or shared memory, local memory in different terminology, and it's shared across the device. So if SIMD, if I've got work launched here, this SIMD unit, it's using more than 64 vector registers. I'm borrowing from these other three, and it can't launch work. So I talk about how many waves can be launched. If I'm using all the LDS, then these can't launch. And so those are our compute limiters. If we're using too much LDS or too many vector registers, I can't use all of these. Okay. So we spend a lot of time trying to keep our memory resource usage down so that we can launch more wavefronts. Over here are our scalar general purpose registers in the scalar unit. We don't have the same problem there. So here's an example, no LDS used, no limiter on performance. If we go way out here and we allocate a very large amount of local memory, we can't launch any more wavefronts. If we reduce the memory usage, now we can launch more wavefronts, okay, or work groups. So we want to use local data store, but only so much. Register pressure is slaying, and we talk about register and memory pressure, and it means we're using more resources, and it's slowing down the performance. We don't have enough of those. And if you think about it, a GPU was originally designed for writing triangles to a screen. And so the loops were short. You didn't need a lot of registers or shared memory. Now we're doing 3D, 4D, 6D physics. You're going to be short on resources, memory resources, in comparison to that original load up or application load on the system. So we really want to watch, especially the vector registers. And our work group size, I think of as proportional to the length of the kernel. If I have a 1-line kernel, I'll use 1024 work group size. If I got a 100-line kernel, I'm going to reduce that to 64 because it gives me more memory resources, more vector registers to work. Okay, so you'll hear people talking about memory pressure and register pressure, and they're basically talking about a shortage of those resources. It also happens on CPUs. We just don't pay as much attention there. In fact, there's fewer registers on a CPU, so there's a lot, the compilers do a lot of work to optimize that register usage. So we talked about this occupancy per SIMD. The SIMD is that red rectangle. And if we're using more registers, we're borrowing from the other three. Scalar general purpose registers, those will spill over into vector registers, so they're usually not a limit. But then we have some C++ coder who passes a struct into the kernel that's got 1,000 items in the struct. They're only using 2 of them, but you know, C++ programmers love to throw big data structures at you. Each one of those consumes a scalar register, and so then they find that they're getting killed with scalar register usage. But that's just because there's actually quite quite a bit of scalar registers. It's just because they're doing, they're not paying attention to what's going on their GPU. So the register allocation is done by the compiler at compilation time. You saw that table come out. It can be slightly different at runtime, but it's generally about the same. And we can limit for a HIP kernel, we can use launch bounds the same way we did with num threads and thread limit. So launch bounds we often use to reduce the workgroup size for a HIP kernel. And so you may see some optimization that people do there. And we can often see a 2x performance increase by tuning that. Now, maybe the difference between 128 and 256 is not so great, but 128 and 1024 may be huge. So there's usually a flat part where it isn't too big a difference, but if you get to the extremes, it can be huge differences. Okay, and there's a blog post on the register pressure that you can look at. So generally, compilers will keep data in registers as much as possible. The LLVM compiler is conservative. They don't want to have wrong results, and they haven't heavily optimized register usage. So if you try to put it into a function, well, it gets inline, so it doesn't really save you registers. You would think it would pop those registers off the stack, but that's not what happens. So we avoid things like asserts, mathematical intrinsics. We can move some data to LDS to take it off of the vector registers. We can reuse variables. Restrict keyword can make a huge difference in some cases. In other cases, it doesn't help at all. And only send into a kernel the data you need. You don't need to, load the whole, everything in your physics kernel into the kernel and only use a part of it. Okay, let's look at fusing kernels. So fusing and splitting kernels is really one of your best resources to optimize performance. If I can design my code so it reads an array once, does as much work in that kernel as possible, that's going to be a lot faster. If I write out an intermediate value or read the arrays multiple times like here, that's going to basically mean that I'm increasing how much memory traffic there is. By combining those two into one kernel, I've just reduced the memory traffic. That's really, really key. So I want to design my workloads so that when I bring it in, I do everything that I want to do on it. It may make the kernel very long. It may increase the vector register usage, but that's generally a win. Okay, reducing reads and writes to main memory. Okay. Now, how would you compute the improvement from those on the back of an envelope? Add up the loads, the stores, just count them up, compare it to here. I can tell you about what the performance improvement will be. Okay. So you don't have to experiment writing code. You can just look at it and say, I'm loading it once, twice, 3 times the array size, doing that 1, 2, 3, 4 times the array size. And here I'm bringing in the data. I've got only once, so I don't have the repeated loads of B and A, or the write of C. Now this is actually a reduction here, or using it on both the right and left side. So we're both reading and writing that array. Okay, synchronization isn't as bad as you might think initially within a kernel, but still you want to avoid it. Host side synchronization can be very expensive. And where you'll see that happening is things like memory allocations. When you do a memory allocation in a loop, it's going to go back to the host and it's going to force a synchronization. So you want to move your memory allocations out of the loop. And you can get surprised by this. So this can have dramatic impact because the GPU is getting so much faster. Anything left on the host is going to really be a bottleneck. There are tricks to getting around this. We can use memory pools. The umpire library out of Lawrence Livermore is heavily used for that. So we use a pool of memory and we use it for different uses in the kernel. So I'm not doing an allocation, I'm just using the same memory space for multiple purposes. Using asynchronous memory copies are really important and overlapping, but memory copies with pinned buffers is 2 times faster than pageable memory. So you really want to watch that. We've talked a little bit about atomics, and this for the MI200, we have this unsafe FP atomics. But you really want to watch your use for that. Quite often you can reorder the loop so that, let's say I'm summing all the sides to a vertice. That's going to be an atomic, and I can rewrite it so that I'm looping over the sides, or looping over the sides, reverse the map so that I don't need the atomic. So there's a lot of ways to reverse the map so that I don't have multiple data values being added to a variable. I'm going the other direction. Here's an example of thread divergent, and this is kind of, I don't know how common this is, but it's a very elegant solution to a thread divergence. It's a short divergence, so it shouldn't have a huge impact, but basically by having even and odd are doing different things. You might have that if you're doing complex numbers or some other case like that. Well, if I just have each thread do both the even and odd for each item, I have no thread divergence. I got more work per thread, which is generally good. One work item per thread is a little light. So if I do 2, this is going to improve the performance. So you can look at little tricks like that to avoid the thread divergence and also get more work per thread. And again, you can look at the assembly for this example in Godbolt and see the difference in how much code is generated. One of the really heavy optimizations on the GPU is something we call warp shuffles, where I can move data from one thread to another using a warp instruction. And it sort of uses the LDS, but doesn't use the LDS storage, just the hardware. This can be effective for things like summation. I can sum powers of 2, so it works on a common width, and I can sum like 4 elements into 1 by using this warp shuffle. So that is actually a very effective way to speed things up while reducing LDS usage and vector register usage. Okay, so for the MI300A, there's a few other considerations. We don't have to worry about copying memory from the CPU array to the GPU array, but we still have some penalty for loading the cache. So it's a lower penalty, but not as much as you would have on a discrete GPU. We also have we have different allocators, and these all behave different. And Giacomo has a nice little exercise where he goes through these and compares them. And you have to look at the second use of the array, because the first one may be slower than the later uses of the array. Hip host malloc is not advised on the MI300A, because we don't need to set up that device and host mapping. We're not going to do that. Hip malloc is usually preferred on the for the MI300A, and malloc is pretty good also. We talked a little bit about page size, the 4 kilobyte pages versus the 2 megabyte pages. Hip malloc that always does 2 megabyte. And then we can use different resources for copies. We'll show a little bit of this on the GPU-aware MPI performance. So keep in mind what the performance limiters are for your kernel. And if it's memory bandwidth, well, you don't worry so much about flops, and look at how you can optimize the bandwidth. And then expose as much parallelism as you can for a GPU. Okay, so we have exercises for this. And I'm going to leave this for the exercise part. And this is going an optimization of vector general purpose registers. But I'm going to go into a deep dive here of looking at a 2D matrix transpose and show you how you can optimize this on the GPU. Because it will show you what data coalescing, what we mean by that. And it's basically contiguous memory loads. If every access by the threads in my work group are sequential addresses, it will do one load. If they're scattered, it takes multiple loads of cache. So let's look at how we can do that. So we really have to think about data ordering. We want contiguous data so that we can coalesce those memory reads and writes. So fewer cache lines, that's going to be faster. It also affects the page loads. So a coalesced memory load, all the threads are accessing adjacent data, so we can load fewer cache lines. If we're aligned, it can eliminate one additional cache line that we have to load. And that can have a smaller effect, but it can still be significant. If the data is scattered, you're going to have to do multiple cache line loads, and you're going to lose performance. Once you're in the GPU is very efficient, but it's getting it through the cache system onto the GPU that is usually the difficult. So memory bandwidth limited kernels, we really want to think about these cache lines. We're grabbing all the data, using all the data we're loading. So how do we write coalesced kernels? Well, there's been a lot of argument over the years about whether structure of arrays or array of structs is faster. And in GPUs, we're often using red, green, blue, or XYZ all together. So they'll often use an array of structs. But in physics, we may have X, Y, and Z, but sometimes we're only operating on X. In that loop, we're only going to be using every third value in the cache line. It's going to kill you. And so generally on the GPU, a struct of arrays is going to be better. arrays are just going to be better for the GPU. So fancy structures usually get in the way. Okay. So how do we write a kernel for coalesced memory loads? Well, we have to look at our structs. In this case, our struct is uneven. It's not, the struct itself is not a 64 byte chunk. So the second value of that struct is not going to be aligned. So you can add this pad, or you can add an align argument to that structure. Okay. Some compilers will do this already, and it can trip you up because you think the size is smaller. MPI has a bottom top variable which will help you find out the actual size of a structure. But this is because we're using an array of structs instead of a struct of arrays. Okay. Generally, I put the largest values at the top of the struct and pad at the bottom. So we really worry mostly about strides when we're striding in the Y and the Z direction. We're just not going to get good memory use. Let's look at, so some of the remedies are we can transpose the data, so now it's contiguous, but we have to pay the cost of the transpose. We can use structure of arrays to reduce this issue, or we can stage it through the local data store. And we saw that we can pad or align the structs to reduce the effect of the alignment issue. So, understanding local data store, we have this programmable scratch, programmable cache or scratch memory. Some people call it a scratch pad for the GPU. That is a different kind of memory. It has memory banks. It is not as sensitive to data cache coalescing. So we're going to exploit that here. So the problem with that is if you have bank conflicts, it can reduce the performance when you're accessing two things in the same LDS bank. And we'll show how to fix that. So to sort of reduce the effect of non-sequential memory access, we're going to load a tile into global memory in a coalesce pattern, store it to LDS, and then compute on that LDS, and then write out the data in a coalesced way. Now, let's see how that actually works. And then we're going to add padding to avoid that bank conflict. So vectorized loads can help a lot. So you've got a 2, 3, and a 4 type. And that'll give you a wider load, but it may mean that you have to deal with a remainder, handle a remainder at the end of your loop. So it makes the programming a little bit more complicated. It can improve bandwidth. For shorter types, it can be very effective. So it's noting here, you've got to handle the tails. I've seen actually where it tests to see if your array size is divisible by 2 and calls a different kernel. That may not be worth it for your code, but it can be worth it for a library. Compiler hints can help here. So let's look at this transpose example, and we're going to step through it. I am running a little late here, so I'll step through this fairly quickly, but this is fairly complex stuff here. So we're going to first look at what happens if we read contiguous data. So this is C ordered data, so we want to read contiguous in the sense of a C array. The actual array in the host code is actually a 1D array. So we're actually allocating 1D, but we're treating it like 2D in the kernel. So you can see over here, this is our input. We want to read it 0, 1, 2, 3, 4, 5, but we're going to be writing out 0, 3, 6, 9. So it's not going to be contiguous on the right. And I write a little macro so it looks like a 2D memory access, just to be a little easier to understand. And basically what we're doing is output XY is equal to input YX. And for C code, this is going to be contiguous, not the right. And so when I write that kernel in HIP, you run this and try it out. And it runs a whole bunch of different matrix sizes. And the runtime for this one is 4,500 microseconds. If I switch that over to have the write contiguous and the read striding. Okay, anybody got a guess? Is this going to be faster or slower? Well, we know that writes, it may have to do a load and a store, so we're maybe doing more operations than a simple read. So I would expect this to be slower. So let's look at this code. And when we run that, we're getting 2,900 microseconds. Is that worth it? That's a pretty big jump, just because we've changed the read and write. Now, is this going to always mean I should worry about being contiguous on the right? Well, not necessarily. I may be reading 10 arrays. And so it may be better to be reading the variables contiguous in that case than worrying. I may only write one array out, so it may be better to be read contiguous. But we have another option. We can use that LDS on the compute units to create a small little memory tile. And then we're going to pad that memory tile with this pad variable. And after we load that tile, we got to synchronize. And then we can write out of the tile in a different order than we read into it. And there's some details. What size can I do? Well, you're limited by the workgroup size and the size of your LDS. But because it's 1024, a 32 by 32 tile is as large as we can go. So we write that kernel. You notice this, we're allocating that shared memory, that memory tile. We're going to load it up. We're going to synchronize, and then we're going to write out in the opposite order. And there is a bug in the slides that I fixed in the examples. But basically, I'm going to be outputting the data contiguous. I'm going to be reading the data contiguous. Okay. So when I read the data, it's contiguous here. When I write it, it's contiguous there. And when I do that, it drops the runtime to 2,600. So I've gotten almost a 2x performance increase by just paying attention to coalescing the memory loads. Okay. This is a good exercise to go through. And if you're doing 2D calculations, I could be doing that in the middle on the LDS memory. And avoid this Y when I'm striding, when I'm going in the Y dimension, I can avoid the striding effect. So I can load tiles. Instead of doing an X pass and a Y pass, I'm going to load a tile and operate on it. So how would I do that on the CPU? Anybody know the technique there? So you can block the loops so that you're operating on a tile on the CPU. And that can have the same effect on the CPU. Okay, so you can run that example on the MI210. It wasn't a big performance. Well, on the MI210, we also looked at RockBLAS, and RockBLAS was fairly slow on the 210, but on the 300A, it was much faster. And on the 300A, we got within 70 to 80% of the memory bandwidth of the GPU by doing this. So you can experiment with this and see what results you get. Okay, so we've had our deep dive. We need that break. We need to think about that, and partway through break, let's get some pictures outside.